Okay. Very well. I have enormous I have a pleasure to announce Grahan from the City University of New York. As you know, Grahan is one of the most important names in logic, and it's an enormous pleasure and honor to receive Grahan to talk about precisely about paraconsistent logic. Because it's by consistency and its coverage, learn back. Thank you very much.
Thank you, Matteo. Okay, so no, that's fine. So first of all, let me say thank you to the people who've organised this fantastic event. Itala, Walter, Marcello, and I'm sure there are many, many people. I think this is a fantastic occasion. I'm really impressed with the fact that they've managed to gather such a great group of young logicians and philosophers from all over the world. I think it's a fantastic occasion. So well done, guys. And I'm delighted to be here as part of it. I'm going to talk about the history of paraconsistency. And I think that the invention, development of modern paraconsistent logic is one of the greatest achievements of philosophy and logic in the 20th century, which is when it kicked off. Because it challenges one of the most deeply entrenched dogmas of Western philosophy, namely that consistency is the sine qua non of rationality. It isn't, and we now know that. And it's thanks to the work of paraconsistent logicians that have been involved in developing it. So that's why I consider the subject to be important. I'm going to talk a bit about the history. It's not something that I'd normally talk about, but Itala said, will you talk a bit about the history of dialethism? And I said, well, you know, it's hard to distinguish that. It's hard to disentangle that from the history of paraconsistency. So I'm going to talk a little bit about both. Of course, the subject is enormous, and I'm not going to try to give a comprehensive history of paraconsistency. That's impossible in this time. So it's very selective, and it's kind of personal. So a lot of the comments relate to people that I've known and things that I've done sometimes. So it's not objective. It's a kind of personal perspective on maybe the last 50 years of paraconsistent logic. So that's where we're going. And before I go any further, what I want to do is dedicate this talk to Newton, who's one of the great founders of paraconsistency, as we'll talk more about this. And it gives me great pleasure to dedicate this talk to Newton. I'm only sorry that he can't be here. I understand why. But Newton, if you're listening out there somewhere on the internet, this is for you, mate. Well done. All right, so this is where we're going. I'm going to talk about three aspects of paraconsistency. Paraconsistency properly so-called, dialectism, and then something about inconsistent mathematics. The first section is by far the longest, so don't get too worried if the first section seems to be going on for a long time. Okay, so you've had the introduction now. I'm going to talk about those three topics, then I'll say a few final words, and then we're done. So, first of all, paraconsistency properly so-called. First of all, I'm going to talk about the name, then the meaning, then a little bit about the history before the 20th century, and then some 20th century history. So that's where we're going. So first of all, the name. We now know that the name was coined by Paraconsistent. So since the 1960s and 70s, Newton da Costa had been developing a new kind of logic, and he needed a name for it, and he didn't have a name. So he wrote to his old friend Miller Casada and asked him what it should be called. And Miro sent a very nice letter back, which has now been published, thanks to Itala, I think, and some colleagues. And Quesada suggested a name. He actually gave Newton 3 names, okay? 3 possibilities. One was ultra-consistent, one was meta-consistent. He said those were okay, but I got something a bit better, which is paraconsistent. This is a quotation from the letter. There is, however, another possibility. Use the prefix para, which in Greek means next to. Paraconsistent logic sounds nice, a bit esoteric. It gives a more or less precise idea of what's it about, i.e. logics that are not like classical ones, but are just a bit next to them, because they can be applied to inconsistent systems, and it has the advantage that there is no deforming semantic load. Okay, Newton liked that, so he decided to call it that. And it was first used in public, as far as I'm aware, at the 3rd Conference in Latin American Logic, which was held in Campinas in '76.
Yes.
Okay.
Yes.
So since then, it's been a name, and it's a great name. I mean, when Newton first told me that Miro had invented the name, I always assumed that para meant something different, because in Greek, para can be translated in many ways into English, and doubtless into Spanish and Portuguese as well. But one meaning of para is beyond, as in paradox, beyond belief. And I'd always assumed that Quesada meant para in that sense, so it's beyond the consistent. And I must confess, I still prefer that reading of it, because that's exactly what paraconsistent logic does. It allows you to reason coherently beyond the consistent. So Quesada notwithstanding, I always think of it as paraconsistent logic as beyond the consistent. Okay, so that's the name. Now the meaning. Okay, so when Quesada gave the name to the logic, it didn't have a very precise definition. It was just a name for the kind of logic that Newton had been developing. I think the first definition of what is now fairly standard was actually given by myself and my sadly deceased old friend, Richard Sylvan, as he became, in the late 1970s, early 1980s. So Richard had actually been at the conference in Campinas in '76, which I learnt from the photographs you sent me, okay? I moved to Australia from the UK in 1976, and I met Richard at the first logic conference I ever went to in Australia, in Canberra, in August '76. So I learnt the word paraconsistent from Richard. He'd just learnt it here, okay? So that's how I picked up the word, even though I'd been thinking about the subject before. But he told me, well, this kind of logic's paraconsistent, mate. So, oh, yeah, okay, fine. But as I say, there wasn't a definition, okay? We published some essays, which came out in the early 80s, and we gave the definition, which I think is now fairly standard. So this is it. A consequence relation turnstile on a language L is paraconsistent if, for some A and B of L, A and not A don't entail B, and where that funny symbol is negation. Okay, so in other words, that inference is explosion, and it says explosion is invalid. Okay, and I think that's now pretty much the standard definition. Actually, there's another definition which will make equally good sense, which is this, and I've just changed the indented bit. Namely, for some sigma A and B, you can deduce A from sigma and not A from sigma, but you can't deduce B. In other words, there are bodies of information, axiom systems, theories, whatever, which entail a contradiction, but which don't entail everything. Okay, that's a different definition. It's entailed by definition 1. Definition 2 does not entail definition 1 unless you assume transitivity of deducibility, or cut. So that's cut, which you'll recognize as just another expression of transitivity of deducibility. If you've got cut, then D1 and D2 are equivalent. You can prove it yourself. I'm not going to prove anything in this talk. It's easy to prove. But if cut fails, those two definitions are not equivalent. D2 can be true without D1. Actually, in the text where Richard and I gave this definition, we pointed out that this equivalent definition requires cut. But in those days, cut-free logics weren't very well known and not particularly significant in the paraconsistent tradition. That's why we gave the definition we did, because it's simpler and we were taking cut for granted. That has now changed because what we've seen, I guess, in the last 15 years is the development of cut-free logics, and they've been espoused by people like Ripley and his co-workers like Egre as solutions to the paradox of self-reference. It's absolutely, they give you inconsistent theories, but actually cut fails, explosion is valid. The reason you don't collapse into triviality is the cut fails, okay? So I guess now I would prefer the second definition, but it's probably too late to change. So we're stuck with it, for better or for worse. Actually, I mean, I don't think it matters too much. You know what we're talking about. A little bit of history before the 20th century. A lot of people think that paraconsistent logic is a new invention. It's not. The earliest logic in the West is paraconsistent. Here is a syllogism. It's valid. It's invalid. Some men are animals, no animals are men, so all men are men. That's not a valid syllogism, even though the premises are contradictory. And Aristotle was well aware of this, okay? Here is a quotation from the prior analytics. In the first figure of the syllogism, no deduction, whether affirmative or negative, can be made out of opposed propositions. No affirmative deduction is possible because both propositions must be affirmative, but opposites are the one affirmative, the other negative. In the middle figure of a deduction, deduction can be made both of opposites and of contraries, and then he gives some example, okay? But that's, I'm not going to read the rest of it. He's clear that there are syllogisms with contradictory premises which do not, which are invalid. They don't entail their conclusions, right? So syllogistic is paraconsistent, because it's not a modern paraconsistent logic, but it's paraconsistent according to the definition, right? So where does the principal explosion enter into the history of Western logic? I'm only going to talk about Western logic today. The East is a topic for another occasion. So explosion enters into the history of Western logic about the 12th century, as far as we know. So there was a school of logicians in Paris, the Paraconsistents, because they lived by a small bridge. And it was centered around a English philosopher called Adalbert Bolsham. And it was one of the members of his school, William of Soissons, so presumably he was French, who gave the first argument for explosion. And it's the familiar Duns Scotus Lewis argument, which most of you will know. After that, the status of explosion was somewhat difficult in medieval logic. So medieval logicians nearly always distinguish between formal consequence and material consequence. But they all had several different distinct notions of material consequence, and they couldn't agree on the definition of formal consequence or the various material consequences. So they had lots of different notions of consequence. According to some of these, explosion was valid. According to others, it was not. So its status was kind of, up in the air in medieval logic. Of course, all the great wealth of medieval logic was forgotten with the so-called Enlightenment, and logic just went back to syllogistic. So in the 18th and 19th centuries, explosion was not valid because they just had syllogistic. So explosion became entrenched in logic again, to the extent that it had ever been entrenched, at the end of the 19th century, when classical logic was invented by Frege and Russell. Classical logic has nothing to do with the classics. Okay, that's pretty obvious now, right? The history of the word classical in classical logic is kind of interesting, but I don't have time to talk about it. But how classical logic got called to be classical logic is an interesting story in its own. So explosion is caused value in classical logic. Classical logic is still, I think it's fair to say, the orthodox logic of our day. But no sooner than Principia was off the press, logicians were developing different logics, non-classical logics. Paraconsistent logic is one kind of non-classical logic. And they don't really appear, paraconsistent logics, till mid-century. So they're relatively late on the non-classical scene. But what I'm going to do now is just run through some of the early people who invented paraconsistent logics. And the earliest one I'm familiar with is this guy. I couldn't find a picture of him. His name's Ivan Orlov. He's a polymath. Those are his dates. And he was actually the first inventor of relevant logic, but we didn't know this until about 20 or 30 years ago. So, backwards. He published a paper called The Calculus of Compatibility Proposition in 1928. This was the first relevant logic, and we now call it the intensional fragment of the relevant logic R. So it had only the connectives, negation, and we now call that fusion, joint compatibility. So to say that A fuse B is to say that A and B are jointly compatible, and then he defined the conditional if A then B, as it's not the case that A and its negation of B are jointly compatible. Okay, and that's a relevant logic because actually he's a bit confused about the difference between the conditional and deducibility, but in these logics, both of these things are invalid conditionals, and therefore if you identify the conditional with entailment, then they're both invalid inferences. So he's got first dibs on relevant logic, which is one kind of paraconsistent logic. Unfortunately, his motivation was confused. He thought that he wanted to take classical logic and add a box to it, a provability operator, because he was interested in intuitionism. And he thought that if you added the box of S5, in fact, to classical logic, then you couldn't have excluded middle. Of course you can. So he wanted to have a different account of the conditional so that you could have the box of S5 and excluded middle. Okay, so he was wrong. His motivation was wrong, and that's clear. But in the process, he invented something cool, namely relevant logic. Now, his work fell into oblivion. So we've only rediscovered it about 20 or 30 years ago, thanks to Kostadolchan. And when relevant logics were developed in the 1950s by Anderson and Belknap and others, they were unaware of the work of Orlov. So this was very early, but it gets first claim to relevant logic. Okay, before we leave Russia, let's talk a bit about this guy. And I think this is a picture of him, but I'm actually not entirely sure, but I think it is. So he invented something called imaginary logic, and not much has been translated into English, but the main text is this thing that we have in English, is Logic and Metalogic of 1912 and 1930. And I mention it because he's often cited as a precursor of modern paraconsistent logic. I think that is a mistake because really it's an extension of syllogistic, okay? So you read it. He's got syllogistic logic. In syllogistic logic, there are two kinds of predicates, is P and is not P, and he adds a third, is P and not P. All right, but it's an extension of syllogistic. And so all the inferences that concern the syllogistic predications are exactly the same as in syllogistic. So this is not a modern logic, it's syllogistic, and syllogistic, as I pointed out, is paraconsistent. So to the extent that he's got paraconsistency, we had it already with syllogistic, okay? What was novel about Vasiliev was the fact that he thought that there could be situations where things could be P and not P. But he's very clear that that cannot happen at this world. This happens only at imaginary worlds. So if you want to put that into modern terminology, he's thinking about impossible worlds. So if Vasiliev is anything, he's not a precursor of paraconsistency. He's a precursor of the modern theory of impossible worlds, which is not quite the same thing. All right, so the next person who published a paper on paraconsistency was this guy, Stanislaw Jaśkowski, Polish, obviously. He published this paper called Propositional Calculus for Contradictory Deductive Systems in 1948. His thought was that information is chunked, depending on who tells you the information. And he thought of each chunk as the contents of a possible world in S5. An inference is valid if in every interpretation, where every premise is true at some possible world, the conclusion is true at some possible world. So it's not preservation of truth of a world, it's preservation of truth at some possible world. And if you go that way, then this form of explosion fails, and therefore adjunction fails. So these are sometimes called non-adjunctive paraconsistent logics. The idea was taken up by Scott and Jennings in Canada, Rescher and Manner in the United States, but this is the origin of non-adjunctive paraconsistent logics. The next person on the Rogues Gallery is a Swede, Sören Haldin, who published a book called The Logic of Nonsense in 1959. Okay, so Haldane has a three-valued logic with a middle value, and it's true, false, those are the usual values. There's a middle value T, which is a fixed point for negation. So if you negate a B, you get a B. And it's designated. So you can have both A and not A designated where some things aren't. So explosion's going to fail. Now, what was his motivation? Well, he was interested in nonsense, statements that are literally nonsense. What are his examples? Well, he tells us things like the liar paradox. So he takes the liar paradox to be a nonsense statement. And so he applies this three-valued logic. Now, why you should expect nonsense statements to be designated is another matter. It's not obvious, right? The natural thing is to be undesignated, but let's pass over that. The notion of a many-valued paraconsistent logic was taken up later by several people, Frank Senho, Mike Dunn, myself, we know many valued paraconsistent logic. As is already clear, paraconsistent logic is not a natural kind, okay? Virtually any technique you can use to construct a modern non-classical logic can be made into a paraconsistent logic somewhere or other. Okay, so the next person to produce a paraconsistent logic was an English audition, Tim Smiley, in this paper, Entailment and Deducibility in 1959. It was a sort of filter logic. You take the valid classical inferences and you filter out the bad guys. And who are the bad guys? Well, validity must hold non-vacuously. So you don't want your conclusion to be a logical truth. You don't want your premise to be a logical falsity. So you filter out those guys. Okay, so a valid inference is one, leave the thing in brackets for a moment, such that if it's classically valid and the conjunction of premises is not a contradiction and the conclusion is not a classical tautology. Why do you need substitution instances of those? Because you need logics to be closed under substitution. And that clause makes a difference. Okay, so that was Smiley's definition. And you can see that these two inferences are valid. This one, because it's a substitution instance of if P, Q, therefore P and Q or R. This one, well, it speaks for itself. And notice that you put those two together with transitivity, then you get explosion. An explosion is not valid because, well, that's a contradiction, right? Or it's conjunction is a contradiction. So in this logic, transitivity fails. And this is the earliest version of non-transitive paraconsistent logics, although it wasn't really taken up till much more recently. But that's the origin. Okay, so next, Richard Routley and Val Routley. Richard and Val were working on the semantics of relevant logic. So when Anton and Belknap and Orlov axiomatized relevant logic, it was just an axiom system, it had no semantics. And Richard and Val, in their earlier work, gave us semantics, which made it a paraconsistent logic in this paper. Semantics, first degree entailment, 1972. So each world, W, it's a world semantics, comes with a mate W star such that, whoops, that's a typo. W star star is W, right? It's an inversion. And not A is true at W, just if A is not true at W star. Classically, you'd say W, right? But here, it's the mate W star. And so there can be worlds where both A and not A hold, or neither A and not A hold. So this was a logic with truth value gaps and gluts. Of course, the idea that a modal operator requires a world shift in its evaluation is obvious. This was the first time anyone had suggested that negation requires a world shift in its evaluation. And that idea was taken up later by a number of other logicians like Dunn and Greg Restall. So that's the origin of that move. And now we come to this guy, okay, who I've already mentioned. So Newton started to develop paraconsistent logics. It first occurred in his doctoral thesis, this thing, which I confess I've never had the pleasure of reading. The first book in English is 74. And what seems to be driving, at least what you get in the 1974 paper, is the thought that what you want to do is dualize intuitionistic logic. So in intuitionistic logic, you can have things that are neither true or false, but you can't have things which are both true and false. And the motivation, Newton's motivation, seems to be, let's dualize that. Let's have things which can be both true and false, but they're either true. So you've got no violations of excluded middle, but you have got violations of non-contradiction. Why did Newton want to do that? Well, again, it's pretty obvious from the 74 paper. He was interested in investigating inconsistent theories, specifically mathematical theories. And this is the first paraconsistent logician I've mentioned who had that motivation. And it's an important motivation, and I'm going to come back to it in the third part of the talk. So when Newton developed his paraconsistent logics, it didn't have semantics. Semantics was found a little bit later by Da Costa and Alves in 1977. And the trick here is to take negation to be non-truth functional. So if A is false, its negation is true. That bit's pretty regular. But if A is true, not A may be true, it may be false. So it's non-deterministic. And so you can have A and not A both true. Okay. Also, a feature of Newton's logic, so these are the C systems, is that you can express the consistency of a formula in the language itself. So you've got this ball operator, and A ball is red, A is consistent, and it's defined in the obvious way. Now, these ideas were taken up later. The notion of a non-truth function negatum was taken up by Didrik Battens in the early 80s, mid-80s, yeah, by Arnon Avron a couple of decades later. And the idea that you have a ball operator was, of course, taken up by a number of the people who are present today. Walter, Marcel Lowe, and Zhao. I'm here. Okay. With their logics and formal inconsistency. So, I mean, what you're seeing is that all these early ideas of how you get a paraconsistent logic were taken up and developed later. Okay. I'm going to leave the history there. I've covered really one of the first generation of paraconsistent logicians. An enormous amount has gone on since then, but I'm going to stop the history there because I want to talk about other things. So let me just make a few final remarks. As I said, I learned the word paraconsistency in the mid-70s from Richard Silver and Richard Rowley. And at that time, we realized there are people working on paraconsistency all over the world. And what we did was we decided to write or edit a book where we got all the people, at least all the people who were alive, who were working on paraconsistent logic, to put papers in. We wanted to make paraconsistent logic a self-conscious movement. And that collection of essays came out in '89. It was finished about '82. It was just that there was a right lot of stuff up in getting it published, which I'll go into over a beer if you like. Okay, so, okay, thank you. After that, we decided it would be a good idea to have the first World Congress on paraconsistency. Now, Australia was not a good place to have it because it's remote. So we wrote to Diderik and said, hey, Diderik, how about having it again? And he said, yeah, I'll do it. Thank you, mate. So the first World Congress on, I'll show you a picture in a minute, later. The first World Congress was held in Ghent in '96, and since then there have been 5, 6 more all over the place. Brazil, France, India, Australia. I think the next one's in Mexico, is that right? Yeah, okay. Oh, in Poland last year. Guess what? I was there. Jeez. Okay, so there's no organising committee for the World Conferences on Paraconsistency. It's an anarchist association. It's great. Okay, whoever wants to do the next one says, I'll do it. And it happens. Magic. Okay, so let me finish by saying something about this. Paraconsistent logic had a really rough ride when it was invented. Logicians and philosophers went, you can't do that in logic. I mean, contradiction, inconsistency is very heart of logic, isn't it? All right. So it had a really rough press. And if I get time, I'll return to why. However, as far as mathematicians went, the matter was settled in 1991. When the category for paraconsistent logics was added to the mathematical classification scheme used by Math Reviews and the Central Bank for Mathematics. And this is one of the editors, Andres Caicedo, who wrote to me like this. The class 03B53 was added in 1991, both with the description changing slightly in 2000. We revise and update the MSc every 10 years. The reason for the class appearing in older papers as Zentralblatt is that they continuously change the classification of all papers to reflect the current version of the MSc. At Math Reviews, on the other hand, we try not to add new classes to old papers already in the database or to change the classes used originally to try to preserve the historical record of how papers originally was used. And then there's an exception. But the point is that in '91, both the Zentralblatt and the American Mathematics Society added the category to the official classes of mathematics. End of story as far as the mathematical story goes. Of course, a lot of philosophers still didn't like it, but mathematically, the subject was closed in '91. It's legit, as I'm sure you're pleased to know. All right, so that's, let me turn to dialethism. Okay, so first of all, let me have a bit of clarification. Paraconsistency, I've just told you what that is. Dialethism is the view that essentially some contradictions are true. I'll come back to that in a second. Trivialism is the view that everything is true. Now, if you want to be a dialethist and you think that some contradictions are true, and you don't want to be a trivialist thinking every contradiction is true, you better use a paraconsistent logic for obvious reasons. So dialethism entails that you'll want paraconsistency, but the converse entailment is not valid. There are many people, including people in this room, who endorse paraconsistent logics who are not dialetheists. And, you know, in fact, I gave you a bunch of founders of paraconsistent logic just now. None of them was dialetheist, at least at the time of writing. Richard Routley became one later, but that was after that paper. So all the founders of paraconsistent logic were not dialetheists. Okay. So you need to distinguish. I'm not a founder. I'm in the second generation. So, okay, let's go through the same thing again. First the name, then the meaning, then a bit of history. So the name. The name was coined by Richard Routley and myself when we were starting to work on this stuff in the late 1970s. And the name is dialetheism. It's a barbaric Greek neologism. Di to aletheia, truth. It's a two-way truth. And we coined that because we wanted a nice name. So we went to the library at the ANU and looked on every dictionary we could find, you know, the Greek, the Latin, the Jewish, the Hebrew, the Irish. We couldn't find a name. So in the end, we had to make one up. And we took our inspiration from this guy, okay? In the remarks on the foundations of mathematics, he says, why should Russell's contradiction not be conceived as something supra-propositional, something that towers above the propositions and looks in both directions like a Janus head? The proposition that contradicts itself would stand like a monument with a Janus head over the propositions of logic. And that's from the remarks on the foundations of mathematics. Oh yeah, that's right. Something that looks both towards truth and falsity. Dialetheism. So it's ugly, but we coined it and it's kind of stuck, which is okay. So as I say, it was coined by Richard and myself in Australia in the late 70s. And let's move to the meaning. But actually, this is a picture of the Australian Logic Group in the late 1970s. So there's Richard Sylvan, there is Bob Meyer, there is Chris Monson, and there's yours truly. In those days, I had hair. All right, so I think that the first precise definition of dialetheism was, I gave it in my book, In Contradictions, in the 80s, and it's this. The notion of a true contradiction is at the heart of this book. Awkward as neologisms are, it will therefore be convenient to have a word for it. I will use dialetheia. So to avoid any confusion, let me say right at the start that the dialetheia is in any true statement of the form A and it's not the case today. There you go. Nowadays, I think I'd take out the and. I'd just say a pair of propositions, A and not A, that are both true. But the book assumes a standard account of conjunction, so this is equivalent. So just note, all it says is that some contradictions are true. That's all. It doesn't say anything about truth or what truth is. Let me just say that something is often said to me about dialetheism. And I'm going to quote you, Walter. I'm sorry. I'm not taking Walter. I'm not singling Walter particularly. It's just that I had his text in front of me when I was writing this. Okay. So he says the dialetheist claims that some contradictions are ontological in the sense that they are due to some inner contradictory essence of reality. Or in other words, that reality, in order to be correctly described, demands pairs of contradictory propositions. Well, what's after the dash? It's fine. But the thing that comes before that, I have no idea where that comes from. It says nothing about ontology. It says nothing about inner contradictions, the essence of reality.
That's why you say other words, not in the same.
Well, okay, if that's what dialetheism is, I'm not a dialetheist. Okay? If you want to read stuff about reality being inconsistent, I'm not even sure that makes sense. If reality is composed of stars and tables and chairs, saying it's inconsistent is simply a category mistake. Okay? To make sense, you need some kind of correspondence theory of truth, and I have never endorsed a correspondence theory of truth. Indeed, in the book In Contradiction, it endorses a rather strange view of truth called the teleological account of truth. I'm not going to tell you what that is, but it is not a correspondence theory of truth. And in another book, Doubt Truth to Be a Liar, I run through all the standard definitions of truth and point out how they're all compatible with dialetheism. So let me just say it one more time so I don't hope to hear it not again. Dialethism is simply the view that some contradictions are true. What does true mean? Your choice. Okay. So that's dialethism. Sorry to single you out, Walter, but I do suspect this view comes from Brazil, actually, but I'm not sure of where it comes from exactly. The view that dialethism says that reality itself is inconsistent.
I cannot say. I think it's somewhere in the encyclopedia, Stanford Encyclopedia, perhaps not well worded.
Yeah.
Very possibly.
Because you're talking about truth.
Very possible.
Sorry?
Right? You're talking about truth. Some contradictions are true.
Yeah.
Right? So presumably, those contradictions reflect something about what's going on.
Yeah, that's true.
So it's not unreasonable.
No, I mean, if something's true, reality makes it so. In that sense, if they're true contradictions, then the world is contradictory. But that is not to say that the world contains inconsistent facts or states of affairs or whatever. I mean, look, if anything is true, the world is such as to make it so. So if by world you just mean what Wittgenstein means at the start of the Tractatus, all that is the case, that's fine. But as I say, you do not have to be a correspondence theorist to be a dialethist. All right. So a bit of history before the 20th century. Of course, the principle of non-contradiction is stated by this guy. For the same thing to hold good and not hold good simultaneously at the same thing and in the same respect is impossible, given any specifications which might be added against dialectical differences. So Hipparchia is a man. Hipparchia is not a man. She's a man because she's human. She's not a man because she's female. That doesn't count. That's silly, right? That's what that last clause is there to get rid of. Now, in the Metaphysics Gamma, there is the kind of canonical defense of the principle of non-contradiction, and it's terrible, all right? And modern commentators agree on this. There's one long argument which is so long and tangled that commentators cannot even agree on what it is, let alone that it works. And then there's a bunch of sort of throwaway arguments, and the most obvious thing about those is that they're ignoratios. What they argue against is trivialism. It's not the case that all contradictions are true. And of course, a dialectist can be perfectly happy with that. So these arguments are terrible, right? Despite that, they establish the principle of non-contradiction as orthodoxy in Western philosophy. So much so that I don't really know of any new arguments for the principle of non-contradiction since Aristotle. Western logicians simply took it for granted. It's kind of interesting that virtually every other Aristotelian claim has been denied, got rid of, rejected, or at least problematized since Aristotle. The principle of non-contradiction is kind of the last bastion of Aristotelian philosophy. Okay, so, okay, then let's skip that. I have more time. Okay. So I think it's fair to say that dialectism is seriously challenged, Hegel aside, by the Australian Paraconsistent movement starting in the 70s. Okay, I think Richard and I were the first people to seriously push it, and the first statement of it was in my book, In Contradiction. First statement of defense of it was in Contradiction. Now, I mean, dialectism is often taken to be a view about the paradox of self-reference. And indeed, that was one of the original driving forces, and it was a prime example of dialectism. But dialectism as such has nothing essentially to do with the paradox of self-reference. It just says that some contradictions are true. It doesn't tell you what contradictions are true. Of course, you know, the theory of dialectism has been applied to the paradox of self-reference, but it's been applied to many other things. Theories of motion, the theories of laws, theories of limits of thought. Let me give you one where I think dialectism is the most transparent. So suppose you've got a couple of laws. One says that all people in group X have the right to do Z. No persons in group Y have the right to do Z. This is perfectly consistent. unless and until someone turns up in groups X and Y, call that person A, then A both does and does not have the right to do Z. Okay, now, how does this contradiction arise? Well, it's bloody obvious, right? Because legislatures can't make some things true. They can't make it true that pigs fly, for example. What legislatures can do is give people the certain rights or take certain rights away by fiat. Okay. And this dialethia arises simply because a bunch of people has passed certain laws. Now, once you take that to heart, you can see that dialethism is to do with language and the world. To make something true in general, you need language with meanings, and you need the world to behave in a certain way. So to get a legal dialethia, you need the language of the judicial body, of the legislative body, but you need the world to behave in a certain way. You need some person, A, to come along, who's in both X and Y. That's an empirical fact. It's about the world. So, as I was saying to Octavio, I mean, the world, if something's true, the world has to cooperate sometimes. But, okay, this is nothing about the inner contradictory nature of the essence of reality. It's just about some poor bastard showing up who's in groups X and Y, right? All right, that's all I'm going to say. Let me turn finally to inconsistent mathematics. So, Newton is distinctive amongst the originators of Paraconsistent logic because he was driven by the thought that what we want is to investigate interesting, inconsistent theories, and being a mathematician, he was particularly interested in mathematical theories. We now know there are lots. Newton is not, and never was, as far as I know, a dialethist. He wasn't interested in mathematical theories, which were inconsistent because he thought they might be true. He thought they could be mathematically interesting, and he was right. It's quite possible to have an interesting mathematical theory based on a non-classical logic. So, for example, the theory of smooth infinitesimals is a theory which requires intuitionistic logic, essentially, and has clear mathematical interest. You don't have to be an intuitionist to think that. Same for paraconsistent mathematics. Anyway, so Newton had this idea that you want to investigate interesting mathematical theories. So, okay, maybe I should have said this. This is another quote from Wittgenstein, made in 1930. Indeed, even at this stage, I predict a time when there will be mathematical investigations of counter-like containing contradictions, and people will actually be proud of having emancipated themselves from consistency. Okay, so let's talk. So do
you have the reference for this book?
Not in my head. Ask me later. I'll give it to you. Okay. This wasn't published till after his death, but it's made in the 1930s. Okay, so after Newton had invented paraconsistent logic, he published a number of papers on inconsistent set theory. So the 1974 paper has a long discussion of a paraconsistent version of Quine's NF, for example. And he worked with a colleague, this is Ida Arruda, publishing a number of papers on paraconsistent set theory. And what made them interesting was that they did not simply quarantine the paradox of set theory, they actually investigated the properties of inconsistent sets because they're kind of interesting. And there's a really nice paper by Ida and Dirac in 1982, Russell set versus the universal set in paraconsistent set theory. Okay, this is one of the very interesting papers in early paraconsistent set theory. Now, paraconsistent set theory is difficult because there's this thing called the naive comprehension scheme. Every condition determines a set. And it's that drives the paradoxes. The trouble with naive comprehension is not simply that it gives you contradictions, it gives you triviality. Because if you've got a logic which has this principle, contraction, you get triviality without negation because of Curry's paradoxes. Now, all the set theories that Newton and his co-workers investigated, as far as I'm aware, use contraction. So they couldn't have this. And in some sense, the holy grail of paraconsistent set theory has always been something which has this as an axiom schema. I mean, it appears to be a priori true. That's what drives the bloody paradoxes, right? And even if you don't think it's a priori true, the fact that it's what drives the paradoxes makes it particularly interesting. So even if you have Newton's view, he would have to find set theories in which you've got the naive convention interesting. But it was left to later logicians to come up with theories of set theory which had this principle. Richard showed that you could do this for elementary set theory in the early 1980s. That it was non-trivial was proved by this guy in the early 1980s. Okay, this is Ross Brady, an Australian logician. That showed that it didn't do too much. Namely, it's not trivial, but it didn't show that it did enough. I mean, could it prove all the standard results of cardinals and ordinals? No one knew. And that question lay on the table for 30 years and was finally resolved by this guy, Zach Weber, who is American but now works in New Zealand, who showed that given an appropriate version of naive set theory, that is with the comprehension schema, you could prove nearly all the standard results of transfinite set theory. It's a brilliant piece of work. Okay. So that's set theory. Okay, let's move on to arithmetic. So this is von Meyer, and he discovered some very interesting facts about relevant arithmetic. If you formulate arithmetic with an underlying relevant logic, not classical logic, then it has models which are kind of interesting. They render true every theorem of piano arithmetic, but they have some quite spectacular properties. For example, they can be finite. How can that be the case? Well, they're inconsistent. So with Bob's work, it became clear that there were interesting facts about inconsistent arithmetics. And you don't have to think that inconsistent arithmetic is true. We know there are lots of classical non-standard models of arithmetic, and they have a very interesting structure. And what we now know is that there's this whole new realm of non-standard models of arithmetic which are inconsistent, and they too have a really interesting structure. There it is. See? Okay, that's the structure, and I'm not going to tell you more about that because I'm nearly out of time. But these do have connections with paradox, because this is the Gödel sentence, right? A sentence which says there's no proof of B. In classical, if you use classical logic as a basis for your arithmetic, the Gödel sentence is, of course, neither provable nor refutable. But if you use one of these paraconsistent logics, paraconsistent arithmetics, then the Gödel sentence and its negation are both provable. So we're playing the other side of the fence, not neither, both. And this is obviously connected with the paradox of self-reference, because this is, in a very thinly disguised form, is the lie paradox. So what the philosophical upshot of these inconsistent arithmetics is, well, that's still being discussed, but those arithmetics bear on the significance of the Gödel results. Okay, last example, I'm going to talk about geometry. And the main work on this has been done by Chris Lawson. You saw, I pointed out a picture of him earlier. So geometry is kind of interesting. So, because there are inconsistent geometries, just as there are non-Euclidean geometries. They often involve inconsistent numbers. So take the real plane, or just this unit square, and divide it into two parts, a left and a right, and let's suppose that there's a dividing line. Let's suppose it's the line x equals 0. What are we to say about things on the line? Are they in left or are they in right? Well, of course, what I've just said doesn't determine the matter. It's an open question. But if you arrange things for L and R to be symmetrical, then this line has got to be both in L and R. And we said that they were disjoint. So if you allow a paraconsistent description of the situation, here is what you can have. If x is less than 0, so you're in L, the point xy is in L consistently. If x is greater than 0, it's in right consistently. And if x is 0, it's in L and R, which are disjoint. So that's a contradiction. And you may think, wow, that's kind of boring, isn't it? It has a rather cool application, namely the mathematics of impossible pictures. So look at this guy. Often we use mathematics to describe the contents of pictures, right? But this is an impossible picture. How do you formulate it in mathematics? Well, look at this plane here. It's horizontal, right? So when you describe the geometry of this picture, anything on this plane has got to be horizontal. Now have a look at this plane. It's vertical. So anything on this plane has to be vertical. Now have a look at this boundary on both planes. So it's got to be horizontal and vertical. That's a contradiction. Of course it is. That's how you know this picture is impossible. All right? But this is an example of that inconsistent boundary situation I showed you just now. So one application of inconsistent geometries is precisely the geometry of impossible pictures. Okay, so now I've finished. So look, I've looked back at some of the stuff in the early years, and as far as mathematics goes, the later years of paraconsistency. As I've said, I regard this as one of the greatest developments in 20th century logic and philosophy. Whatever you make of some of the substantial philosophical issues we've talked about, logicians will write a great deal about this period in years hence. In fact, I mean, some of it's been written by Itala and Evandro here, thank you, in their book, okay? But there's going to be a lot more to be said in due course. I think we've only just started. There's so much potential in the subject. The subjects I've been talking about obviously have further possibilities, and there are many, many possibilities that we haven't even thought of yet. So I think that paraconsistent logic, it's really all to play for. I've talked a little bit about the history, but the future is going to be much more important. So that's the thought I want to leave you with. Actually, what I'll leave you with is this picture, which is those present at the first World Congress in Paraconsistency. So this picture was in Ghent in 1996. And you'll recognize some of the present company there. If you look hard. Okay, it's not a great picture. Let me see. Oh, actually, Richard Sylvan died about 2 months before this conference. So he's not. It's very sad. Let me see who's there. Florethia Senho, Steve Reed, Chris Mortensen, Jean-Paul Van Bendigem, moi, Dominic Hyde. Is Italy there? Italy, were you there?
I was there at the meeting. My first,
No, Nisa wasn't there.
my first meeting.
Okay. I think Walter there somewhere. Where are you, Walter?
I think I have the yellow jacket, yellow jacket.
Oh, yeah. You're right up front. Good on. Okay. Anyway, so I dug this out of my archives. I thought you might like to see it. Anyway, thank you.
Thanks for your talk. Very interesting, as usual.
Abelio, yeah. And spare.
Okay. Well, thanks for your talk. Very interesting, as usual. I have a remark and a question about whether or not the deliberism is ontological. Because deliberism is for some proposition A, for some sentence A is true and not A is true. If we accept that truth depends on reality, so the aletheia depends on reality, in the sense that it is grounded in reality. There is something in reality that makes A true and not A true. And usually we say that things that depend on reality are ontological.
Yeah, but all truth is like that. There's something special about dialethism.
Sorry?
All truth is like that. I mean, things are true because of language and the world. So if
Yes.
something is true, it's usually because the world makes it so. And if that is all you mean by inconsistent, about reality being inconsistent, I'm cool with that. Okay? It hasn't, but it's not a correspondence theory of truth, as is clear from the legal example. The thought that reality, in some sense, is inconsistent is just dialethism plus a correspondence theory of truth.
Okay, but the second part is, actually, we do not need correspondence theory of truth, we don't need state of affairs, we don't need facts, we need only the G-schema. We don't need even a metaphysics of properties. Because if you have the T-schema, you have, for example, an object A that satisfies the predicate P, and an object A that satisfies the predicate not P.
Correct.
So I think it would be almost obvious to say that this object is a contradictory object.
Well,
And this object belongs to reality.
of course.
So why don't you use the word ontological here?
Well, because it would be particularly misleading. Because as you've just used the deflationary version of truth, okay? You've just used a deflationary account of truth.
Yes.
So dialethism is compatible with a deflationary version of truth, okay? Now, if, for example, this poor person, A, is in groups X and Y, then she has the property Z and doesn't the right to do Z and the right not to do Z. Okay. And that's so because of the deflationary theory of truth. Now, in one sense, the deflationary theory of truth tells you nothing about reality. How you determine the right-hand side of the T-schema holds is a whole other question. You could, if you want, be a coherence theorist.
No, I like a reading of the T-schema that understands the right side as a relation between the word and the language.
That's fine.
Okay.
No, I like it too. But all I'm saying is that the T-schema is compatible with the coherence theory of truth. Okay? In that sense, there's nothing realistic about it whatsoever.
Yeah, Professor, thanks very much. Could you say at least a bit about Hegel?
Yeah, so the principle of non-contradiction has been high orthodoxy in Western philosophy. There are a few people who stand out, and Hegel was one of them. And Hegel scholars tend to froth at their mouth when I say that Hegel is a dialethist, right? But this is from the logic. Common experience says that there's a host of contradictory things, contradictory arrangements, whose contradiction exists not merely in external reflection, but in themselves. External sensuous motion is contradiction's immediate existence. Something moves, not because at one moment it's here and another there, but because at one and the same moment it is here and not here. And that here, at once is both is and is not. Yeah, this is a dialectic.
Actually, it's stronger. It's the ontological version.
Well, he says they're true. Hegel's theory of truth is it's not a correspondence theory. What exactly it is, Hegel scholars argue about. Okay. Also, let me just say that in his lecture on the history of philosophy, when he discusses Eubulides, the inventor of the liar paradox, he gives his own solution to the liar paradox. And he says, I quote, it's both true and not true.
Okay.
Hegel was a dialethist. One of the few exceptions between current day and Aristotle.
you said that in Paraconsistent arithmetics you can prove the given sentence. I imagine that you cannot exhibit.
You imagine what?
What I'm asking is if there is
Yeah.
some way to exhibit. The
Well, you mean find the code number?
construct.
Yeah, you can.
Yeah.
Absolutely.
Okay.
Because it has a standard Gödel coding. So, you just figure out what the Gödel coding of the sentence is. It's easy. It's just what you do in classical logic.
And well, what I think is that maybe consistent mathematics could be maybe just like when we discovered imaginary numbers or something. There is another kind of ontological beings which we actually is not consistent with what we have been considering as the being. But yeah, somehow it helps you to understand all the problems
Okay.
in what we actually consider to be.
I think you're close to the truth. The ontology of numbers is, of course, a highly contentious issue in the philosophy of mathematics. But imaginary numbers are no more imaginary than real numbers. They have exactly the same status, whatever that is. And I think the discovery of paradoxical entities in set theory has something like the significance of the discovery of real numbers or imaginary numbers. They're just entities, whatever those are, of a kind that we didn't really think about before. So I think, as I said in an early paper, the discovery of inconsistent mathematical objects is one of the greatest mathematical discoveries since the discovery of reals.
Nice.
Here, here. Thanks for your time. More than 10 years ago, you published papers on that was logic.
Yes.
I was wondering whether you were still interested in that line of Paraconsistent logic.
Okay. To be honest, I haven't done much since then. I mean, this was a fetcher for Newton, and I was invited to contribute a paper. So I thought, what the hell can I talk about? And dual paraconsistent logic is where, and if you look at a Kripke model for intuitionistic logic, negation and the conditional work forwards. Okay? If you do the dual thing and go backwards in the ordering, you get an operator with the dual properties, or operators, negation and conditional with the dual properties. So just as Newton, I think, was trying to dualize intuitionistic logic, that is the obvious, and that is an obvious construction to achieve that end. So that was all I was doing there. But a lot of other people have worked on these logics since then. I'll give you some reference if you want to email.
That's great. That was a very stimulating talk. I have a question about the first part. And I wonder if it's not worth distinguishing by people who stumble on image system that have consistent features, and those who have a clear motivation to achieve something in the practices. Because as you point out, some of the very early groups were interested in other things.
Sure.
Some didn't even develop a system per se.
Oh, they all develop systems.
Sorry?
They all develop systems of paraconsistent logic.
Well, depending on what you mean by system. Right?
Well, they had axiom systems or model theories.
No, specifics didn't have. Right? He had ideas about objects.
Yeah, but I didn't count Vassiliev, I discounted him. Orlov did, Yashkovsky did, Haldane did, the Routlers did, Smiley did, Newton did, of course. Now, I agree that Newton's motivation was distinctive and important, but all these guys had motivations, and I sort of indicated what those were. So it's not that they didn't merely construct formal systems, they were each motivated by something. Very different things in each case.
Yeah. Well, I guess the other thing is then what counts as the margin.
Well, I mean, they had axiom systems, and later on, all these systems had model theories.
Yeah, later on.
Well, the many-valued logics came with a model theory, right? Relevant logic, and modal logic came with a model theory only later.
Yeah, because I think what I find contribution of Newton is they only have position of practical calculus. So it's the whole package, right? So you have it. That seems to be fairly unique, right?
Well, I agree that he was the first person to be interested in investigating inconsistent theories, deliberately inconsistent theories, leave Frege out of this, okay? And he was the first person to do that, and that's great. But it wasn't as though the other people were entirely unmotivated and didn't have motivations, they did. They were just not that motivation.
That's the one thing I don't show. Yeah, the issue is not only having motivation, but developing lots of systems to achieve the motivation.
Yeah, there's a whole class of many valued paraconsistent logics as well. I mean, in a sense,
Yeah.
once you've got one paraconsistent logic using a particular construction, most of them are clearly and obviously generalizable, and most of them are clearly and obviously extendable to a first order logic in a very natural fashion.
This should be done. I mean, it's not obvious how to do it in the sense that you may get actually surprising limitations.
Sometimes, but
So that has to be done.
well,
The fact that we did counters.
yeah, look, but all of these things have first order logics which are relatively obvious extensions. Now, how many of the logicians did that? Newton did that, I agree. I think Tim Smiler's technique applies obviously to first order logic. I'm not sure whether he did or not, but anyway, look, I'm not quite sure to what extent we disagree. I mean, Newton's originality, I think, was in precisely the motivation and of course the systems he developed. And the motivation was the investigation of inconsistent theory. And in that, he was clearly the first.
Last question.
For the talk. Okay, I understand that the definition of data is not coming to a particular account of truth. I would like you have a particular account of truth. So which one?
I have a very stable view on this. When I wrote Incompletion, I presented something called the teleological truth. Namely, the truth is the goal of certain cognitive attitudes like belief. And I still think there's a lot to be said for that. But that's the only theory of truth I ever endorsed. And it's clear there's nothing particularly ontological about that. It's to do with the telos of cognitive states.
Thank you very much.